This PPT is visible.
Yes, sir.
Yeah, the slide is mechanics of material, right? Yes, anyone can give the answer?
Yes.
Right?
Yes, sir.
Yeah. Okay. Okay, I'll start. Yes. Good afternoon, one and all. Now, in the last lecturer, in the lecturer 2, we discussed about what do you mean by mechanics of material, right? The main aim of mechanics of material is to study the behavior of a body. There's a what type of body? A deformable body. When it is subjected to an external force, right? How the body behaves when it is subject to an external force, how the body is deformed, right? The main objective is to study the effects of external load on a deformable body. The effects caused by forces acting on a body are internal force and deformation. When you consider a body subjected to an external force that produces what initially it resists to deform, then what you call it internal effects is occurred. In the internal effects it contains two things. One is internal force. You can see that in the figure, in the first figure, it is a consider a body, okay, it may be rectangular, it's a bar, right? It's subject to an external force, that is F. Initially it resists the force that produces what internal force. Here see the in the second picture, the internal resistance force is Fn. External applied force is capital F. Internal resistance force is Fn that acts over where? Cross-sectional area, right? Then after again that internal resistance force occurred over a cross-sectional area, that you called as a stress. From the internal force occurred over a cross-sectional area, the term will get a stress. Even if you increase the load, in the first figure see that even if you increase the load on the bar, what happens? First initially that resists the force, then after that even increase the force, the bar will undergo change in dimension, that we call as a deformation, right? When the change in deformation to the original deformation will be called as the term called as strains. Now our aim in this subject, mechanics of material, we are going to determine how the body behaves. Your body is deformable body. How the deformable body behaves when it's subjected to an external force, right? We are going to, our ultimate aim is to determine stresses induced in the body and what are the strains are induced in the body. That is the main aim in the subject. Later we'll come to know that why do you want to study the stresses and strain. Okay, so before going to design any component, we should say that when a load applied on the component, the load the body has to withstand the load. How do you say? By determining stresses induced in the component. Whatever the stresses induced in the component is less than the allowable or working stress, then you can say the body can withstand the load, the design is safe, the design of the body is safe. Later we'll come to know that. Okay, now just we should know write these things. This is we discussed in the last class, right? And also we discussed what do you mean by stress. Stress is nothing but the intensity of internally resistance forces acting over a cross-sectional area that resists the shape of the body, that we call as a stress. Now what it measures, if you say so I am stressed, means what it measures? It measures the intensity or magnitude of forces acting over a cross-sectional area, right? It measures, because force is a vector quantity, it has both magnitude and direction. But stress measures intensity of forces, nothing but magnitude of forces acting over a cross-sectional area. Now if you say stress is acting on a body, means it requires three factors, such as one is magnitude, second one is direction, and third one is area. As you know, mathematically, how do you represent stress? Stress is directly proportional. Stress is equal to is a ratio of load by cross-sectional area. This is a mathematical representation, a mathematical formula. Stress we can notation as sigma. That's a normal stress. It may be tensile or compressive. Load we can represent as F, or sometimes we can represent as P. Load is in Newton, right? Then cross-sectional area you represent as A. That is a unit of stress is Newton per mm square. So in the last lecture, I gave the one example that practically a man is standing on the floor. So the what is the load of the man is nothing but what is the force or weight of the man is nothing but mass into acceleration due to gravity. For example, if you consider the mass of the body, mass of the person is 60 kg into mass into acceleration due to gravity is how much? 9.81 meter per second square, right? Then a 60 into 9.81 meter per second square that acts vertically where vertically downward. That's the weight acting vertically downward on the floor, right? Here, what is the here the foot the here is standing on the two legs, right? Whatever the where the contact area is there, contact area is the foot area. So two foots are there, right? Two into the area of the foot that is contact over the surface area. Now you can calculate what is the stress induced on the ground here or on the foot here. That's a force by cross-sectional area, right? Okay. That is stress is acting on the foot. Suppose instead of standing on two legs, suppose if you stand only on one leg, what happens? Cross-sectional area is reduces. Once cross-sectional area reduces, the mass of the person remains same. The weight of the person is same, right? When cross-sectional area decreasing, whatever stresses is increasing. Now, one important thing you observe here: the stress is directly proportional to the load, inversely proportional to the cross-sectional area. Means as the load is increases, as the weight of the person is increases, the stress acting on the foot is also increases. And another one is as the cross-sectional area is decreases, whatever stress is also increases. That is a statement. Stress is directly proportional to the force or load and inversely proportional to the cross-sectional area. Right? I think you understand. You did this exercise. Who has done this one in last class? Yes. Yes, Grishma, right? Grishma is
Yes,
there?
sir.
Okay.
Yes, sir. Yes, sir.
Okay. Now this is the physical meaning. You should understand what is the physical meaning of the stress. Or if you suppose if you're carrying a more weight, suppose you're carrying a box, chairs, etc. What happens? The weight is increases. Once a weight is increases, you can feel on the foot stress is increases or decreases. Grishma.
Sir?
Suppose if you're standing right on the floor, if you
Yeah.
carry box or some weights, if you're carrying a bucket, right? What happens? The weight
Okay.
is increases or decreases.
Weight increases.
Once weight increases, what happens? The
Stress increases.
stress is also increases on
Increases.
the foot, right? Now that is the main statement. Stress is directly proportional to the force,
Load.
inversely proportional to the
Cross-sectional
cross-sectional area. Okay, thank you, ma'am. Then last class we discussed about types of stresses also. Based on the type of forces acting on a body, stresses are classified as three things. One is tensile stress, compressive stress, and another one is shear stress. How do you say this? The tensile stress means, now consider that this is a rectangular a bar, right? Now here the two forces are acting away from each other. Where it is acting on centroidal axis, right? The two equal and opposite forces acting away from each other. Then what type of forces the bar is subjected here? Tensile force. The tensile force occurred over a cross-sectional area is called as tensile stress. Once the body is subjected to a tensile force means the body is what happens? It elongate, means increasing dimension, increasing in the length dimension. And the other two dimension what happens? Decreases. The lateral dimension decreases. That you can see here. The dotted line shows the original body, the shape of the body and dimension of the body. Once you apply a load, two equal and opposite forces acting along the centroidal axis. What happens? The length increases, other two dimensions decreases, right? That stress induced in the body is tensile stress. Second one, if the forces act two equal and opposite forces acting towards each other, towards each other, then that type of force is called the compressive force. Here what happens here, it is decreasing dimension, decreasing the length dimension. Once it is decreasing length dimension, other two dimensions what happens, lateral dimensions are increases. That's what is a compressive force. The stresses induced due to compressive force on the cross sectional area is called as compressive stress. And third one is shear stress. The two equal and opposite forces acting tangential to the surfaces. Acting on tangential surfaces. That is called as a shear stress. Shearing. Shear force. The shear force acting over an area called as shear stress. Right? In the previous lecturer and this lecturer, I made a small corrections here. Now these are definitions for tensile stress, compressive stress, and shear stress. Again, tensile and compressive stress is also called as normal stress. Why do you call it as normal stress? Means the stresses are acting here perpendicular to the cross-sectional area. That is called as normal stress. But shear stress acting where it is not perpendicular to the surface area. It is parallel to the area. It is parallel to the surface area. That is called as a shear stress. Now, normal stress is nothing but a normal load by cross-sectional area. Shear stress is nothing but shear force load by surface area. So remember these two definitions. They are very, very important. Again, shear stress notation, what we use here, tau. Right? Shear force is a surface area. Also, you can represent A, or you can use A suffix S. That measured in, what is the unit here? Newton per mm square. Right? Now, again, this slide is not in the previous lecturer. Now, see that. Now, here, take a bar. What happens here? Two equal and opposite forces acting away from each other on the body. That is called as a first one is. Yes, what is the first one? Likita is there. Likita N.
Yes, sir.
Yeah. Now, you give me the answer for this mark. And the PPT is visible.
Yes, sir.
Yeah. Now, in the first one, I'm moving cursor here, right? Now, on the body, what type of force is acting here? Here, two forces equal and two equal and opposite forces acting away from each other.
Yes,
What
sir.
type of forces here? It undergoes elongation, right?
Yes, sir.
Yeah. What type of force it is? What type of force it is?
Sharing.
No.
Forces.
First one it is. Yes. Aradhana is there.
Yes, sir.
Now tell me, Aradhana, what type of force it is, ma?
First one, sir.
Yeah. First one.
Tensile stress, sir.
Yeah. Tensile force is acting on your body. Then the body is subject to what type of stress? Tensile stress.
Tensile stress.
Now second one.
Compressive stress.
Yes, compressive stress. Now two forces are acting towards each other along the central axis, the compressive, right? Now
Yes,
third
sir.
one I will not discuss here. Now this is what we call as a torsion. Torsion means, I think once you wash the cloth, then I want to remove the water from the cloth. How do you will do? We'll go for twist it, right?
Yes, sir.
Go for twisting movement, apply twisting movement. That is called a twisting. The twisting is also a what type of stresses induced here? Here change in shape of the body. Means that is a shearing stress acting on the body. That's called a torsion. Clear?
Yes, sir.
Yeah. Now Aniket is there. Aniket. No. Now Pratik Anand.
Sir, Aniket, sir.
Aniket.
Yes, sir.
Now see the Aniket here. Fourth figure here. I
Yes.
think you are seeing this. I'm moving the cursor.
Yes.
Right? Now
Yes,
here
sir.
it is called as a rivet or a pin here.
Yes.
One side I am applying force this side, another one is applying force this side. Means this is a pin here. One
Yes.
is applying force like this, another one is applying force like this. What type of force it is?
Tensile only, sir.
No, not tensile. Here tensile you are applying on this rod, but here the element is component is here the pin it is in vertical direction is there, right?
Yes.
Yeah, that body is subject to what? Now this is a pin here. I am applying one force here, another force here.
Don't know, sir.
You don't know. Okay, the best example for this. Okay, so bolts. If you consider a bolt here, one side you are applying here one plate here another plate. Both the plates you are applying a load here away from each other. But the
Shear,
limit of
shear,
the bolt,
sir,
yeah,
shear.
is separate of shear. Is a force is acting over the surface area. It is shear. Okay, now this one I will not discuss in the previous classes. See that. Now consider this is a one body. Now it is subjected to a transverse load or a movement. What happens here? You can see the video here, not the. Okay, you can see the PPT also or in video. I think video is not visible. I think because power has gone.
Excuse me,
Okay.
sir.
Is it visible?
Excuse me,
Video
sir.
is visible.
No, sir. The video is not visible.
I think power has gone here. Okay. Now,
Excuse me, sir.
if
Sir,
subjected, if you
someone
take,
is.
Sir, I have a doubt, sir.
okay, tell me, ma'am.
Sir, can you please give us example between shear stress and tensile stress by like can you explain by giving examples?
Okay, giving example. Which one here? One is tensile, another one is
Shear, shear.
shear.
Like,
Okay.
can you
Suppose if you take best example, tug of war. I think you are almost all the boys are played that one, right? Tug of war. You know the tug of war?
yes, sir.
Okay, so you are what we are doing here? We are pulling the what is the rope, right? Yes or no?
Yes, sir.
Yeah, the rope is subject to what type of force? Tensile only, right?
Tensile
Yes.
force, sir.
Away
Both.
from each other.
Yeah. Second best example for shear is, for example, if you are walking, right? If you are
Yes.
walking and running, whatever your foot is contact over the floor, right?
Yes, sir.
Again, if you move forward, one more step forward means what happens here? What type of force acting on the floor or on the foot? Yes, if you want, you can physically practice here. If you physically can do. What type of force acting on the foot when you walk or run on the floor?
What type of force, sir?
Sir,
Yeah, what type of force acting on the floor or on the foot when you walk or run?
Compress.
No, no, not
Compressive.
when you walk or
sir,
run.
sir,
Shear
in
force,
shear,
frictional force. Yes,
shear,
sir.
the both the forces are acting in opposite direction, and someone is holding that in between, sir.
Which one?
Shear.
Shear. Okay, another best example for
And
I can give shear forces. Suppose if you cut the vegetables or the bread, right? Or if you cut the, okay, if you take a piece of apple, if you bite it, right? Then those are what is force acting on the surface area. That is called shear. You can see here also the normal stresses are one is tensile, compressive. Now see the here shear stress, right? I think you see in my PPT.
Sir, I have another doubt, sir.
Ah, yes, ma'am.
Sir, while doing hand wrestling, what kind of force is expressed, sir?
Which one? Which one? Sorry.
Hand
Pardon?
wrestling.
Hand?
Wrestling.
Hand wrestling. Oh,
Yeah,
that is a compressive only.
that is compressive.
Yeah, compressive only.
Okay, sir.
Yes. Any other doubt? Okay, shall I continue?
yes, sir.
Yeah, okay. Now you can see this is another one is the torsional. When you go for take a cloth, the wetted cloth, if you want to remove the water, what we will do? We will go for twist it, right? That is called the torsion. And best example for torsion, if you go for tightening the bolt with the help of spanner, how do you go for tightening the bolt? We'll go for the spanner, we'll go for tightening. That is a on bolt subject to what? Torsion. That is a twisting movement. Again, comes to stress means shear stress is acting there. And third one is one more, another one important one is bending stress we called as. What is a bending stress means? Suppose if you see it means is a better you can clear observe here. Okay, 1 minute. Okay, I think it is visible this one, the component.
Yes, sir.
Yeah, now see that this is the one component. It's applied to an external movement. Now what happens this body? It undergoes bend, right? Yes or no? Are you seeing this component? What I am showing here? Is someone now it is subject to a bending. Once it is bending here, at the central axis, we call it neutral axis, their stresses are 0. Above the neutral axis, what happens? The fiber undergoes tension. Below the neutral axis, means central axis, the fiber undergoes what? Compression. Again, these are the other types of stresses we call as. That is called as a bending stress, right? You can see in the slide also, once on the central axis, above the central axis, the fiber undergoes tension. The fiber undergoes tension, means elongate here. Here, inward here, the fiber undergoes compression, means it has to decrease in dimension, right? Now, this is called as a bending stress we call as. The bending stress are, it may be tensile or compressive in nature. On other types of stress here, torsion or twisting movement. That is what I explained here. In the wetted cloth, if you twist it, if you want to remove the water from the wetted cloth, what we'll do? We'll go for twist it. That is called twisting movement. What type of stress is acting on there here? Shear stress. And last one, this one already we discussed, bearing stress. One component rests over the another one. See the duster here is placed over the another one. Now this is the first body, this is the second body. First body is placed over the second body. Now second body is subjected to what type of stress here? Bearing stress. That is bear the first body, right? But actually, we will not study this one, the third one. Okay, these are other.
Excuse me, sir.
Yes.
I have two doubts, sir. First one is what is longitudinal stress, and another thing is what is the principle behind shear stress?
Okay, longitudinal stress. It may be either tensile or compressive stresses.
Example for longitudinal, sir.
Longitudinal stress examples. Okay, if you take a rubber, if you apply a load on the rubber, means along the axis, along the length direction. Longitudinal nothing but length direction it is. What happens
Okay.
here? It elongates, right?
Okay, sir. Okay.
Whereas if you take
Sir,
ah,
what's the principle behind shear stress, sir? Can you give me like an ideal example to explain those shear stress?
shear stress, the main behind shear stress means shearing. Due to shearing, what happens here? In tensile and compressive, what happens? It will change the dimension. In tensile,
Okay,
it increases the length. In compressive, forces acting on a body, it decreases the dimension, right?
Okay, sir.
But
Okay.
the shape will remain same. Shape will not changes in tensile and compressive force acting on a body. Shape means if it is rectangular shape means rectangular only. Circular
Okay.
body means circular only. But when it comes to shear stress, what happened? It will changes its shape, but it will not
Yeah.
deform. It will not the body will not change any dimension. Only what happens? Change in shape. See
Okay,
the
sir.
one more slide I will show here for better understanding.
Yes,
Yeah,
sir.
now we can see here in this one. In the first one, is body the dotted line shows original body. When it's subjected to a tensile force, the continuous
Yes.
thickness you can see that it is increasing length, decreasing dimension. Means
Yes,
it
sir.
changing dimension, but not the
Yes.
shape. When it comes to
Okay.
second picture here, shear strain, what happens here? The square shape it is body. When shear force acting on a body, bottom side it is called as it is fixed here. Now the square becomes what here? Rhombus. The shape changes, right?
Yes, sir.
Yeah, always material failures due to shear stress only. Why means
Okay, sir.
whenever the body changes its shape, then failure occurs, right?
Okay.
If
Yes,
you want
sir.
this example,
Sir, like washing clothes, no, sir.
washing clothes. Yeah. Any other examples?
While we rub that brushing that clothes, sir.
Yes. If you take any body, if the body is failure means it will change its shape only. If you suppose if you take, yeah, when you take a plastic bag, if you go for pull it, plastic bag for pull it, its shape will changes, right? Then only it failure occurs. It fails to with a standard load, right?
Sir, but like you gave example of walking on the road for shearing stress.
Yeah, yeah.
Yeah, but there is no change of any shape or anything. Like how can that be
Shear
example for?
force is acting on the body. Suppose if you walk on the mud or in okay in the seashore, if you walk on that what you call as a sandy okay floor, now you can see the change shape is occurred or not in what we call as in beaches, right?
Yes, yes.
But on road or in on road or on mud road or in tar road, that the body will withstand that load, shear load. That will not change any shape.
Sir, but our that slipper bottom will get rubbed, no, sir. That sole
Rub,
bit.
yeah, it will rub. Means due to changes its shape only. That's why it will reveal. That is called as wearing. It is. Again, so many factors will come here. Yes. Any other doubts? No doubts. Shall I continue? Yes. Shall I continue?
Yes, sir. Yes, sir.
Okay. Yeah. Now our next topic is strain. That is another very important term. First term is stress. We discussed what do you mean by stress, what are the different types of stresses, how the stresses are acting on a body, right? When it comes to strain is nothing but what? Before going to define strain, first we should know about deformation. What is the meaning of deformation? Means when a body is subjected to an external force, suppose if a change in dimension takes place in the body, dimensions are nothing but length, width and thickness. Those are the dimension of a body. If circular cross section means length and diameter, right? If it's circular cross section, okay, yeah, this is a marker pen. If you assume it is a circular cross section, if the marker pen is there, yeah, if a circular cross section is nothing but what are the dimensions here? One is length, another one is diameter, right? Okay. Now, when a body is subject to an external force, it change in dimension of a body, a member, when it's subject to a force, then it called as a, whether it is increment dimension or decrement dimension, depend upon the type of force active, whether tensile or compressive nature. Then the body is undergo what? Deformation, right? Any doubt about the deformation? Yes? No doubt? Yes. Next, second term is strain. Now we'll go for defined strains. What do you mean by strain? Means the change in dimension to the original dimension of a member. Change in dimension to the original dimension of member we call as a strain. So what it measures? It measures the intensity of deformation. How much deformation, how much change of dimension of a body takes place when it's subject to an external force. That measures the strain. For example, suppose from morning to evening, suppose if you work in a what is an agricultural field, or if you did some any work, physical activity work, at the end of the day, what will say? Today we are very tired, means more strain is occurred on our body. What happens in strain is occurred in a body means the body will go for shrink it, right? Say yes or no, anyone?
Yes, sir.
Yes? Yeah, that is what we call as a change in dimension of a body or change in dimension of our body also. We'll go for shrink it, our face will not glow, again we'll go for down our neck, right? That is a strain is occurred on a person, that we call it. That is called as a
Sir,
strain.
excuse me, sir.
Ah, ah,
I have another doubt, sir. Sir,
yeah,
this
yeah.
strain in whenever strain occurs, the body doesn't deform, right, sir? Doesn't go to its original state.
That is later will come. That is the two types of deformation. The one is elastic deformation, other one is plastic deformation.
Okay, sir.
Okay.
Now in this slide we are talking about.
Only just strain. Definition for strain. Change
Okay,
in
sir.
dimension to the original dimension of a
Okay, sir.
member will be subject to an external force. Okay.
Sir, even in shear stress, the dimension will change, right, sir?
No. Dimension will not change. See the figure. Okay. In next slide, I will come here. Now see
Okay,
what
sir.
is the dimension from here, same dimension here only. Only the shape will change.
Yeah, shape is also a dimension, right, sir?
Shape is nothing but geometry, related to geometry. Is there a circular shape, rectangular, square, pentagon, hexagon, what you study in the engineering
If,
graphics? That is
yes,
the
sir.
shape. regular
If
shape.
volume doesn't change, if volume doesn't change, it's shear stress, right, sir?
Don't go for your volume. Okay, the volume will again come to picture later on. You can
Okay,
consider only two-dimensional body. Okay.
Okay.
Yeah. Shall I continue? Any other doubt? Okay, now comes to strain. How do you mathematically represent strain? Strain we can symbolically represent as epsilon. Stress, normal stress we represent as sigma. Shear stress we can represent as tau. Now strain is a normal strain actually is represented as epsilon, right? What is epsilon? What is strain here? It's the ratio of change in dimension to the original dimension. Whenever change in dimension takes place here, when a body is subject to an external force, see here, when a body is subject to a tensile force, the dotted line shows original member or original body. The continuous thick line, what we see here, deformed body. When a body is subjected to a tensile force, it increases length, right? Whatever other two dimension, lateral two dimension width and thickness is decreases. The dimension decreases in lateral dimension called as. It increases length, right, due to the tensile force. Now what is the change in dimension here? Final dimension, final length minus initial length. Original dimension is as a initial dimension, initial length. If you take that, we call as a longitudinal strain we call as. Okay, now best example you can see here, along here circular rod I consider here. The initial length of the rod is L. When it is subjected to an external force P, right? So what happens when you subject to external force P here? It changes its dimension. How much it change in dimension here? Delta. How do you get delta? Final length, that is L plus delta, that is the final length, minus initial length is L. Now L get cancelled, only what we get here? Delta. That is change in dimension here, delta. What is the original dimension is L. Yes or no? This strain is called as longitudinal strain because the dimension takes place only along the length direction. Clear? Any doubt regarding definition for strain? Okay. Now comes to types of strain. There are three types of strain. One is axial or longitudinal strain. Why it called as axial or longitudinal means whatever the load is acting here along the length direction, right? It may be tensile in nature or compressive in nature. If it is tensile in nature, what happens? Length increases. Other two dimension decreases. If it compressive in nature, length decreases. Other two dimensions, width and thickness, the dimension increases, right? So if I take only longitudinal strain means, longitudinal strain is where the change in dimension takes place along the length only. That is change in length by original length, right? Second strain is called as a transverse or lateral strain. Why do you call it as a lateral means? If you are applying a load on tensile in nature along the length direction, that is the length direction L.
Sir, we can't see PPT, sir.
Sorry?
We can't see that page.
You can't see that? Yes, pardon?
We can't see that page, sir.
A PPT you can see, right?
Yes, sir. Yes, sir.
Okay.
Yes, sir. Yes, sir.
I will explain in the PPT only. Okay, see the other two dimensions. Here on the length direction, force is applied, right? It increases dimension along the length direction. What happened? Other two dimension, width and thickness, right? This is a width and thickness. What happens? The dimension is decreases. This is called as a lateral dimension, right? The strain induced here, that lateral or another term is also called as a transverse strain. How do you define lateral strain here? Change in lateral dimension to the original lateral dimension. For example, here I'll consider as a diameter. Suppose here length is dimension is L, lateral dimension is circular rod, it is D, diameter. Now change in diameter to the original diameter, that is called the lateral strain. Go for longitudinal strain means change in length by original length, right? Any doubts regarding about longitudinal strain and lateral strain? Is any doubt? Best example, you can take the rubber, elastic rubber. If you apply a load, tensile load, what happens? Length increases. That's a longitudinal strain. Change in length by original length. Whatever, at the same time, diameter of the rubber is decreases. You can see that. That is called the lateral strain is occurred. There's a change in lateral dimension to the change in diameter to the original diameter. Any doubt? Now you go for shear strain. Strain due to change in shape or distortion. Distortion is called as a nothing but what do you mean distortion means change in shape of a body. When body is subjected to shear force, that is called as a shear strain occur. See the what is the shear strain here? This is the first example I show is a normal strain. This is one is the change in shape of a body. Earlier is a dotted line is a square body. Now when shear force acting here, it become a rhombus. Right? These are the different types of strain. Yes, any doubt? Shall I continue? Okay.
Yes, sir.
Now the next topic. Now you understood what do you mean by stress and what do you mean by yes. Any doubt? Okay. Now we understood what do you mean by stress and what do you mean by strain. Now we'll go for stress strain diagram. This is a very important topic. Okay. So you can for exam point of view also you can remember this one because most of the questions appear 4 marks, 6 marks. Draw a stress strain diagram for some particular material. Okay. Now here first I will take the specimen here. The tensile test. Now once you come to a laboratory, material testing laboratory, now you can see that the circular cross section rod it is. It's a what is the initial length? We will measure only from here to here. Means it this whatever the extra portions are there, these are we use for gripper purpose. Okay, to hold the jaws firmly. For that we use this gripper purpose, right? Only we measure the original length of the bar is L naught. Okay, what type of cross section here? Circular cross section. The initial diameter is D. When the body is subjected a tensile force here on the both side, a tensile force is occurred. What happened? So before applying tensile force, first we'll go for draw the stress strain diagram. The x-axis shows a strain, y-axis shows stress. Clear? So always y-axis we represent vertically is a dependent variable, right? X-axis always we represent as independent variable. Am I right? When you plot a graph, always x-axis is an independent variable. Y-axis is dependent variable, right? Now we go for stress strain diagram. If there is no load acting here on the component, the first figure here, what means the stress induced here? Is there any change in dimension? No. What is the meaning of? Okay, I will take this the formula also. Better we can understand. Okay. Yeah, first, so if you apply a load on the component, okay, the force is there, cross section also there. If there is no applied on the force, there is no force means what is the stress is? Stress value is how much? 0. No load means the F is equal to 0. Stress is also 0. Now we will start from this curve. If there is no load means what about strain? Is there any change in dimension takes place? No. Again we will start from the origin. That is the O, right? Now as the load increases on the both side of the specimen, as the load increases, what happen? First, initially the body is resist. As the load increases, F is increases, cross-sectional area is constant. Now what happens? Stress also increases. Now as the stress increases, what happened? See the second sketch here. See the second sketch. Okay. Now what happens? It increases length, right? Dimension. The length dimension is increases. Once length increases, the change in length by original length, the strain also increases. See that how that it increases there? It increases linearly. Up to what point? Up to point A, right? Now as the stress is increases, strain also increases. How it increases here? It increases linearly. That behaves the straight line equation. Y is equal to mx plus c. What is y here? Sigma. M is nothing but slope, right? X is nothing but what? Independent variable, epsilon, plus c. C is nothing but what here? 0, right? Y is equal to mx only. Means sigma is equal to m into epsilon. It behaves a straight line equation. Up to this point, the point A is called as a proportional limit. See the proportional limit. Now what do you mean by proportional? Means stress is directly proportional to strain. It is linearly proportional, right? That is called as stress is directly proportional to strain. That is called the proportional limit. And second one, again, if you increase the load on the component, now it reaches one more point. That also it is a linear scale, straight line. That point B is called as a elastic limit. What do you mean by elastic? Means suppose if you increase the load, the deformation also changes, the stresses induced also increases. Now if you remove that load, at this point B, what happens? The body comes back to original shape and size. That maximum point, you can say that the body will come back to original shape and size. The maximum stresses induced. That point B is called as an elastic limit. Best example, if you take a rubber, elastic rubber, if you increase it and leave it, it comes back to original shape and size, right? That point is called as an elastic limit or elastic point. Again, if you increase the load, what happens? Here, see the from B to C, a small curve here, not a straight line here, small curve. Means if you increase the load, the body will not linearly proportional. Stress is not linearly proportional to strain. Right, that is called a non-linear proportional. Once it is non-linear proportional, means it goes to yield. Means what means? It goes to permanent deformation, plastic region called a permanent deformation. At point C, if you remove the load, it will not come back to original shape and size. It will come somewhere here. Okay, some already deformation takes place in the body. That point C is called as a yield point. Yield. The point D, again, if you without increasing load, what happens? The material is deformed. Why the material deformed without increasing load? Means once it reaches yield point, okay, material without taking a load, it deform more. That is called as another point is called as a yield point. That is a lower yield point here, means lower stress value. And C point is a ultimate yield point, and another second one is lower yield point or upper yield point and lower yield point you get. After the once you get point D, again if you increase the load on the component, okay, screen is disabled, 1 minute. PowerPoint is visible. If someone has given an answer.
Yes, sir.
No, sir.
Yes.
Yes, it is
If
visible.
someone can give the answer.
Visible. Hello.
Hello.
Yes, sir, it's visible.
Hello.
Yes, sir.
Okay, something I think went wrong. Okay, 1 minute. Okay. Now PPT is visible.
No.
Someone say yes or no?
No.
Okay. Now again, if you see the third picture here, if you increase the load, what happens here? The cross-sectional area is reducing here. Now again, the stress is not linearly proportional here, non-linear proportional here.
Sir,
Now later we
PowerPoint
come
is
to
not
dotted
visible,
line.
sir.
We are non-linearly proportional here. Okay,
PPT is not visible,
someone
sir.
has to mute yourself.
Sir, PPT is not there, sir.
Yes. Now from point to D to point E, again if you increase the load on the component, that is the third one. Okay, stress is not linearly proportional. It behaves a non-linear. It behaves a quadratic equation. Right? What is a quadratic equation? Ax square plus bx plus c is equal to 0. It behaves a quadratic equation. You will get a non-linear curve. Up to where? Up to withstand the maximum load. Maximum stress here.
PPT
Yes.
not visible.
PPT is not visible?
No, sir.
Okay, 1 minute, ma'am. Now it is visible?
Yeah, yes, sir.
Okay. Now from point D, again if you increase the load on the specimen, what happens? Stress is not linearly proportional to strain. It behaves a non-linear. It behaves as a quadratic equation. The quadratic equation is ax square plus bx plus c is equal to 0. Up to what extent? Up to it forms a necking. What is the necking here? In our body also you can see the necking here. What is the necking here? It is a reducing cross-sectional area, right? See in the third figure you can see the reducing cross-sectional area. Up to that the material can withstand the maximum stress. Again, even though if you apply more load here at the point E, that is the third figure, what happens? It reduces the cross-sectional area, it completely breaks. Now the load is, stress will not increases, but deformation is more. Finally it comes to what point here? Rupture or breaking point. This is what the stress strain diagram for mild steel. The point E is called as the ultimate point. From this you will get ultimate stress, and point F is called as a breaking or fracture point. Now suppose if you get a question, draw a stress strain diagram for mild steel. Now this picture you should draw. There's a continuous thick line is there, right? That continuous thick line, that graph, that geometry, sorry, that figure you should draw. What's the dashed line here? Now what we draw here is the engineering stress. What do you mean by engineering stress strain diagram is, see that engineering stress, you know the stress formula is load by cross-section area. If you take load by original cross-section area throughout entire the specimen failure, up to specimen failure, there's a necking forearm and then fracture occur. Up to that, what area we consider original cross-section area? Means for a first specimen, what we measured a diameter here, cross-section area, same cross-section area you consider here. That stress is called as an engineering stress. For theoretical analysis or what we call as the analytical method, always we consider engineering stress only. Second one is true stress and strain. What is the true stress means? Instantaneous load divided by instantaneous cross-sectional area. Now you can see that in the 4 sketches here, original cross-sectional area is A0. Again, if you increase the load, what happens? Usually length increases, diameter decreases. Now cross-sectional area reduces here. From second figure. From third figure also cross-sectional area reduces. Finally what happens here? Fracture occur, right? Instantaneous means at that time what is the cross-sectional area is there. If you put here, then you will get a true stress. There is a difference between engineering stress and true stress. But true stress actually will not use in our theoretical application, because every time you are going to measure the cross-sectional area. Okay, it's impossible to measure in the cross-sectional area at each time in conducting the experiment, or in the laboratory what we are doing, each time will not measure the cross-sectional area. For that we'll go for use only engineering stress, right? Now that is the figure. What do you see that up to lower yield point, both engineering stress and strain curve is same, and true stress and strain curve is same. Once it crosses the lower yield point, you can see the dotted line. The dotted line shows what? True stress strain diagram. The continuous thick line what you use is a engineering stress strain diagram. It's called as conventional or engineering stress strain diagram, right? Now from this is a 0 origin stands for there is no stress and strain. Point A is called as a proportional limit, means within the proportional limit what stress is linearly proportional to strain. Point B is called as elastic limit. Why do you call it elastic limit? If you remove the load at that point, it will come back to original shape and size. Then point C is nothing but yield point. Yield point means it undergoes a permanent deformation. If you remove the load at the point C, the material will not come back to original shape and size. It will come from here. Already some permanent deformation takes place. Now I think, okay, the sketch is not there here. Okay, next point D. This point C is upper yield point. Why it is upper means maximum yield stress is occurred here. Point D is lower stresses here. That is a lower yield point, right? Best example for if you want to explain point C and D. Okay, the best example if you take a material, the material is made up of a molecules, atomic level. If you apply a load here, suppose one atom is slippage here, one atom come out from the actual material. What happens? The slipping occurred here. Means without applying any load, deformation occurred more. That is a point C and D takes place at that point. Then point E is nothing but ultimate point. R is called the maximum stresses induced here. There is an ultimate stress. And point F is a breakage or rupture strength. Means finally it's the single component become two or more components or two or more body. That is a finally it will not withstand any load, fracture, right? This is a stress strain diagram. And what we can see here, when you conduct the experiment, when it comes to material testing lab, you can see this is a specimen here. Now what is the necking forum here? Once how the material fell here. If you see the cup and cone shape here, this is a cup. Here it is a cone shape. Cup and cone shape you will get here. That is called as that material will called as a ductile material. That we will discuss in later. Okay. Again, this graph also you can see that this and this both are same, right? Okay, this is with actual value I can show here. Is any doubt regarding stress strain diagram? This is a stress strain diagram for mild steel. Mild steel are low carbon steel. A steel having the 0.05 to 0.25, sir, 0.05 to 0.15% of carbon contained in the steel. That is a low carbon steel. Best example for low carbon steel is a mild steel. I think you studied in your engineering mechanics, in the civil elements of civil engineering. Mild steel?
No, sir.
No? Okay. There are three types of steels are there. Low carbon steel, medium carbon steel, high carbon steel. Based on the percentage of carbon present in the steel, we can categorize. You can in detail study in the subject material science. I don't know whether you have the subject or not. Okay. Okay. So just remember the low carbon steel is nothing but mild steel. Again, one more thing.
Excuse me, sir.
Yes, ma'am.
Sir, does this stress strain diagram work for also non-conductors also?
Non-conductor, yes. The later I'll come. For different material, I have one more the slide here. There for different material here. You can see it here. Okay.
Okay. For wood also we can graph like that, sir.
Yeah, not same graph you'll get. Okay, next slide I will tell you that one.
Sir, another doubt, sir.
Yeah.
It might be sound silly, but I must ask, sir. The thing is, why strain cannot go vertical and stress cannot come horizontal?
Okay, one is if you want to plot a graph, we need two parameters. Suppose if you want to plot a graph, y is equal to mx plus c.
Yes.
Straight line or quadratic equation ax square plus bx plus c is equal to 0.
Yes.
In that, one is what you call as independent variable, another one is dependent variable.
Yes,
right?
sir. Yes.
So an independent variable, it does not depend upon anything. If your independent variable varies, how the dependent variable varies, that I want to know that, right?
Okay. So
That
there's
always
another question.
independent variable is represented as x-axis, dependent variable is represented as y-axis.
Yes, sir. Thank you, sir. Sir, there's another question. What is the relation between stress and strain in this graph?
Yeah. That I will come later, man. Okay, because these are all the terms are familiar, interlink it is. First, you should know what is stress, next strain, then what is how it is related. Now I'll come later that one.
Yes, sir.
Okay. Any other doubts?
Sir, can you explain this graph once more elegantly?
Independently. Okay. Okay. Suppose we consider a specimen here. There is no load acting here in this specimen. These two are grippers actually. You can see the grippers here. These two are grippers. No, already it is deformed one only. Okay, throughout the length, the cross section area is same. There is a first one. The length is L0, that is called as a gauge length or original length. What is the diameter here? D. Without applying any load means what is the load? There is no load on the specimen means what is the stress is? Zero. Now we start from 0 here. Without any load here, the body will also not deform, right? Body will not change in dimension. Once a change in dimension is 0 means what is the strain is 0 only, right?
Oh,
Okay.
0, yes, sir.
Yes. Now the curve will start from origin only, 0 only, right?
Yes, sir.
Now
Yes,
as
sir.
the load increases, if you apply tensile load here,
Okay, sir.
as the load increases, right? It's a numerator term. As the load increases, what happens is whatever area is cross section, original cross section area we take only, because it's a constant. Okay, that is called as a engineering stress, right?
Okay, sir.
The area is constant. As the load increases, what happens? Stress also
Same, sir.
stress also increases, right? At the same time, strain, when the load is occurred on a component, dimension also changes, right?
Okay,
Once
sir.
length is increases, length is increases, change in dimension takes place, change in length takes place to the original length. The strain also increases, right? Strain also increases. How it is proportional here? Its proportion is linear proportional. That is called as a straight line you'll get.
Okay, sir.
Yeah, it is a straight line.
Yes,
Up to what limit? Up to the point A, you will get a straight line. That point A is called as a proportional limit. Stress is linearly proportional to strain.
Yes,
Again,
sir.
if you increase the load, it is also a straight line only. From A to B, also straight line only. But the
Yes, sir.
point B we called as a elastic limit. Why we call as elastic limit means up to that
Yes,
load,
sir.
if you remove the load on the specimen, okay,
Yes, sir.
it comes back to original shape and size. The same, if you remove the load here, it comes back to original shape and size. For the first specimen, as it is, it will come here.
Yes, sir.
There is no permanent deformation. There is no permanent change in dimension.
Yes,
That
sir.
point is called as a elastic limit. Again,
Yes,
if
sir.
you increase the load from B to C, you can see that a curve it is, not a straight
Yes,
line.
sir. Yes, sir. Yes, sir.
Yielding means strain is more, but whatever
Okay.
stress is less.
Less.
That is called as a yielding, means permanent deformation goes here. Again, if you
Yes, sir.
remove the load from point C, now it will
Yes,
not
sir.
come back to 0. It will come here, straight line, here parallel to this OA line. It will come here. That is called as a permanent strain occurred here.
Okay, sir.
Okay. Again, if you without increasing the load, again if you not increase the load at the same time, what happens? Deformation is more.
Okay, sir.
Conduct the while conducting the experiment, you come to know that why that it will occurred here.
Yes,
Without
sir.
increasing load, it will deform more. Means strain is more. That's why it comes to again the material will not take the load here. Means it decreases
Yes.
load. That's why F is decreasing means stress also decreases.
Yes.
That's why you can see the curve downward here.
Another doubt, sir.
Yeah.
Sir, this rupture strength is also called as fracture point, right, sir?
Yeah, fracture point, right.
Okay, sir.
Fracture
Sir,
means it is split into two components. It will not
yes, sir.
withstand any load. It's a failure. Yes.
Okay, sir. Sir, another question. What is the use of this graph, sir? Applications.
Yeah, okay. I'll come here. Now see the one is elasticity here. Up to O to B, you can see the O to B. Up to what is the elastic limit. Means if you apply a load up to point B, you can leave that load, it come back to original shape and size.
Yes, yes.
That is called the elastic region. This is a O to O, B and vertical line here. That is called the elastic region. Now from this graph you can see that. Okay. This is the elastic region. So always you'll design a material up to whatever the stresses, whatever stresses induced in the component up to elastic limit only, limit only, or up to sometime yield stress only. Then only the component is withstand the load.
Okay,
Once
sir.
it passes the yield strength, what happens? Permanent deformation occurred. Once permanent deformation occurred, the failure occurred here.
Yes, sir.
Okay. That is called as a plastic region. See the plastic region, you can see the curve here, right?
Yes,
It
sir.
behaves
Yes, sir.
quadratic equation, non-linear. Once it reaches plastic region, that material will failure. I can give best example. If you take a chair, plastic chair you take.
Okay,
So
sir.
okay, one person can sit and leave the chair. We may get
Yes,
1
sir.
year, 2 years, 5 years, the life, right?
Yes,
On the
sir.
same plastic chair, at a time, 2 or 3% can, if you sit on that chair, what happens?
It will break.
It will go bend like this. But I'm taking an example for best example of plastic chair. It will first deform here, permanent deformation. Finally,
Yes.
what happens? Rupture, right?
Sir,
Failure
there's
takes place.
another doubt, sir.
Yeah.
Like for a rubber, there's if a condition like a rubber, huge
Yeah.
rubber, it doesn't have a elastic limit at all.
Okay.
Oh, is there something like that, sir?
No. It also have a elastic limit. Up to load, you apply load and leave it. It comes back to original shape and position. Means it is in an elastic region only. Even if you apply load on the component, if you increase the load, if you not come back to original shape and size. Original shape means the cross section, size means initial length, whatever it is. It will not come back means that is called as plastic. It undergo plastic means permanent deformation. Best example for the both means take elastic rubber, there's elastic region. Take a plastic bag. Best example, take plastic bag. If you apply a tensile load on that, it will not come back to original shape and size. That means
sir.
it undergoes plastic region.
Yes, sir.
Any other doubt? Okay, be familiar with this, but actually we need this one is again we'll explain offline only. If you're not comfortable with the explanation, better go to YouTube and see the explanation for this. Better we all should understand this one. Because all the design of the element, it may be aircraft, spacecraft or mechanical devices, all should be based on this only because material is the stress strength curve for the material. Up to yield strength only we consider. If your material, whatever the stresses induced in the component is less than yield strength, the design is safe. The material can withstand the load. Once it crosses the yield stress, the material will failure. Okay? Yes. Now you can see the stress strain diagram here also. Okay, the same stress strain diagram here. Here what we for the low carbon steel or mild steel. Now you can see the different material. What are the different material is there? Okay, somebody has asked for non-conductive material or maybe hood. Maybe here see the mild steel here. The dotted line is the mild steel. What we see the plot in the previous slide here for aluminum, for cast iron, for so pure aluminum here. Pure aluminum is a there is no yield point here. There's completely it is behaves a similar to a rubber. It behaves as a what is called as a non-linear curve. Similarly, if you take wood also, okay. So if you want, you can search in net, okay, in the Google images. You can see for different material, different stress strain diagram is there. This is for stress strain diagram for different material. Yes, any doubt? Okay, shall I go for next one? Yes. Manoj K is there? Manoj K.
Yes, sir. Yes, sir.
And Manoj K. I think you are playing cricket.
Yes, sir.
Oh. So this is the what you called as adverse effect of online classes. Okay. Now, okay. So some of your friends asked, what is the relation between stress and strain here? Now, according to Hooke's law, so he stated here, within the elastic limit, stress is directly proportional to strain. Up to elastic limit, what is the point B? Right? Stress is linearly proportional or directly proportional to strain. See the equation here. The stress, what type of stress here? Normal stress, because you consider a tensile force, right? Stress is directly proportional to strain. In order to remove that proportionality, what we use a constant E, that is a proportionality constant. Now this is a relation between stress strain relation. Stress is directly proportional to strain. In order to remove the proportionality, we need a constant. That constant is E. E is nothing but what? Proportionality constant. Who derived this? The scientist name is Young's. The scientist name is Young's. Modulus. Modulus are nothing but constant. Remember the word, whenever you say the modulus is nothing but is a constant. Young's, the scientist name, Young's modulus, or modulus of what type of here it is? Elasticity, modulus of velocity. Now from this equation you can see the modulus of velocity or Young's modulus is a ratio of stress by strain. Now this is a relation between stress and strain. Again one more, stress having unit Newton per mm square. What about strain? Strain is having any unit? See the change in dimension millimeter, original dimension also millimeter. Millimeter get cancelled. Strain having, there is no unit for strain. There is no units for strain. That is what stress is. Okay, Young's modulus is equal to is a ratio of stress by strain. Who derived this is a Hooke's law. Hooke's is a scientist name. Yes, someone has asked that question, right? What is the relation between stress and strain? Yes.
Yes, sir.
Yeah. Now this is the relation between stress and strain. Stress is this is called as a one-dimensional equation. One-dimensional Hooke's law equation. Stress is equal to Young's modulus into strain. It's a one-dimensional. Why do you call it as a one-dimensional? Whatever the load we are applying here, in one direction only, right? Along the length direction only. You will not apply the load on transverse direction, right? That's why we call it a one-dimensional stress-strain relationship. Again, remember this equation. Yes, this is already we discussed about engineering stress and true stress. Yes, any other doubts? Okay, up to that I will stop. Next class I will go for material properties and mechanical properties of the materials. Okay, today we discussed about again revision of stress. First we discussed about what is the mechanics of material. Next we discussed about what do you mean by stress, types of stresses and the importance of stress. Physically you can feel it. Okay, next types of stresses. Next example for stresses, different types of stresses, and other types of stresses are bending stresses, torsion or twisting movement, and bearing stress. Then later we discussed about deformation. There is a change in dimension of a member subject to a force. It may be incremental or increasing dimension or decreasing dimension. Then what do you mean by strain? Strain is the change in dimension to the original dimension of member. Okay, remember the formula. And types of strain, one is longitudinal strain, lateral strain, then third one is shear strain. Then there is stress strain diagram for the mild steel. This is a mild steel or low carbon steel. This is a very important topic what we discussed today here. This is a Hooke's law. Hooke's law states that within the elastic limit, there's a point B. Stress is linearly proportional to strain. In order to remove the proportionality, we need a constant. That constant is proportionality constant. That constant is called as Young's modulus. Modulus is nothing but what? Constant. Remember that word. So many modulus will come. Okay. When you go for in detail, okay, Young's modulus, bulk modulus, rigidity modulus, so many modulus will come. Modulus is nothing but what? Constant. Or modulus of constant for elasticity. Remember this equation also. Young's modulus equal to is a ratio of stress and strain. See that in the graph also is a ratio of stress and strain. Okay. Yeah, in the last class I gave some assignment, right? Again, come back to the assignment. Aradhana. Yes, Aradhana is there?
Yes.
Yeah, now tell me, in your home, give me any two examples for any type of stress. Maybe tensile, compressive, shear, torsion, bending, bearing.
Opening a bottle cap for shear stress.
Okay. Next. One example. Second one.
Second one. Stress ball for compressive stress.
Sorry.
Stress.
Desk. In your home appliances, you tell me, ma'am. Okay. Ankit is there? Sorry, Aniket. Sorry, Aniket.
Yes.
Yeah. Now give
Yes,
me
sir.
2 examples for the stresses, types of stresses in your home.
Tensile stress, sir.
Ah.
Okay.
So be fast. Only 5 minutes I have.
Actually, I was absent for yesterday's class, but also I will tell, sir. One.
Okay. Tell me, ma'am. So, remaining students be ready for the answers. Okay, Pratik.
Sir,
Pratik.
twisted stress, sir. Washing cloth, while washing cloth, we will that twist that dresses
The
for
torsion or twisting movement. Okay, ma'am. Next, Pratik. Pratik is there.
Pratik Bharadwaj.
Pratik Anand. Okay, absent. Deepak. Deepak is there.
Yes, sir.
Deepak.
Sir, I'm there, sir.
Yeah, tell me. Give me example. Any one example in your home appliances. Whether it is the components related to a tensile, compressive shear, bending, twisting.
Sir,
So
that.
be
Sir, water tap, sir. Water tap.
water taps are related to what type of forces?
Sir, shearing, sir.
Shearing, there's a twisting movement. Water tap here are called as twisting movement, right?
Yes, sir.
Next, Desi Reddy. So be fast. Desi Reddy is absent. Yes, number 6.
Sir, present.
Ita Shamu, right?
Yes, sir.
Give me example.
Cutting fruits. Shearing.
Cutting fruits, good. Comes under what type of stress?
Shearing, sir. Tangential.
Okay. Next, Rani KS. Is the Rani KS? Is there? Is there? Okay.
Not there,
Anirudh? Grishma? Grishma.
Yes, sir.
Give me example.
Example for tensile stress is guitar string.
Guitar string. Okay, is not a tensile actually. It is a transverse load. We'll consider as a transverse because we're not applying along the axis. You are applying perpendicular to the axis. That's why called as a transverse load. It is. Okay. Okay. Later we'll come to that. When it comes to the beams, okay, there's a transverse load. Okay. Next, Janvi. Janvi is there? Absent. Hiramat.
Present, sir.
Yeah. Give me example, ma'am.
Fridge door, sir. Compressive stress.
Okay. Kavya Shahpur.
Yes, sir.
Yeah, give me example.
Switching on and off of light.
Yeah, switching on and off of light. Yeah, it comes under what type of stress, ma'am? On the switch.
Shear stress.
No. Compressive. You are switching on and off, right?
Yes, sir.
You are compressing. You are acting a force, what you call as towards the body, right? Compressive force. Yes. Lahari. Give me. Yes.
Connecting rods.
Connecting rod. You are going to. Okay, engines. I say engines. Yeah, it is compressive. What type of force? Connecting rod. Yes. Good. No. It's not tensor. It's compressive. On the connecting rod, see the piston and connecting rod. On the piston, pressure is applying downward, right? It's a compressive force. Yes. Good. Nikita.
Sir, elevator cables, tensile stress.
Yeah, elevator cable. When you lift the load in the elevator or in the it's a tensile. Good, ma. Mallana Gowda. Be fast. Absent. Mallikarjun. Manoj K. Naveen S. Nisarga, Pawan Kumar, Pradeep K.
Yes, sir. Sir.
Praveen.
Sir, Pradeep K.
Okay, still you are thinking, my Praveen. Be ready to give answer. Rutuja.
Opening and closing the door of refrigerator.
That already someone has given. Sagar.
Sir, rubber band.
Sorry.
Rubber band.
Rubber band. Comes under which type of stresses now?
Tensile stress, sir.
Tensile stress. Sujit Kumar.
Yes, sir.
Yeah.
Brushing teeth, sir. Compressive stress, I
Yes.
think.
Brushing teeth comes under what type of stresses now?
Yes, sir.
Yeah, what type of stresses?
Compressive stress, I think.
Apart from compressive or brushing the teeth means is what? Is a force acting on the surface area.
Yeah. So
Yeah,
I'm
what?
compressing against my teeth.
First you are applying compressive, then after that when you go for brush it,
Yeah.
it's the shear stress now.
Shear stress.
Yeah, Tejas. Vijay Simha.
Sir, riding a bike.
Who is this Vijay Simha?
Yes, sir.
Yeah.
Riding a bike on road, sir.
Which stress is
Shear
acting?
stress.
Shear.
Shear
Okay.
stress.
Yashwant D. Raj. Yashwant D. Raj.
Yes, sir.
Give me example.
Sir, using sponge for cleaning.
What
Compressive
type of stress acting is?
Compressive stress.
Oh no, using sponge for cleaning is a brushing like this, right?
No, sir. Like when you squeeze it, no, sir. Dimension change.
Compress it. Okay. That is a compress. Okay.
Right.
Yogesh P. Yogesh
Sir,
P is there?
compressive. Sir, air pump. Compressive stress.
Okay. Okay. Thank you, guys. Next class okay. In the next class, we'll discuss remaining thing. Thank you, one and all. Okay. Leave it now.
Hello. Sir, can you please send this PDF, sir? Hello. Hello.
Hello, sir.